Hello everyone, my name is Sarah Studio. Today, I'd like to present our recent work on LTL verification of Bitvector programs. This is a joint work with Chen Bingpang, Daniel Ditch, Eric Koskin, Tong Chandler, Georgios Fotokatalis, and Jun Shi. Now, let me first introduce some background about this topic. In general, a verification task consists of two parts: a program model P and the property phi. While challenges vary in different types of program and also the assertion logic of phi. In our work, we are focused on Bitvector programs and the LTL verification, which includes reachability and termination. There are many cases that we have to reason about the Bitvector programs. And also there are many verification tools that relying on the SMT solvers as backend to solve the problems. In order to verify a Bitvector program, one requires to support the fixed size Bitvector series here. However, there are some problems we have to address first before we go into the verification of Bitvector programs here. The first one is that the fixed size Bitvector series, which is supported by the SMT solvers, use a technique called bit blasting to encode the integer. It introduces a fresh variable for every single bit of that integer. This approach can easily lead to an explanation growth. On the other side, the verification tools like CPA checker Automate have a limited support for the liveness verification over the Bitvector domain. And also LTR verification tasks are absent from the software verification competition. And as for the other categories of verification tasks, there are very limited Bitvector benchmarks. With that in mind, we came up a new way to verify programs with Bitvector operations through the source level translation. We call this technique as bitwise branching. And our approach is that we introduce linear conditional case splits to leverage the linear reasoning in this SMT solvers. And we did a wide range of evaluation about our bitwise branching, and we experiment with the reachability, termination, and LTL verification of the Bitvector programs. And finally, we also developed a binary decompilation toolchain to be the first LTL verifier for the decompiled programs. And we released our toolchain DarkSea and source code and all the experiment benchmarks online. Now, let me walk through an example for a better understanding the problems here, and also show you how to apply our bitwise branching. And in this program, in order to prove the error location at line 6 is unreachable, we have to reason about the if condition R here. And this R is actually related to the bitwise expression on line 5. And if we are tracing back further, this is also related to another bitwise expression at line 3. Tools like CPA checker Automate can verify this safety property only with the support of Bitvector theories here. And with our idea that support the Bitvectors through the linear approximation, and we can approximate the Bitvector operations with linear constraints. This helps us to shift the bitwise reasoning to an integer domain, therefore gaining the various support from the state-of-the-art verification tools. And also this approach can help us suddenly transform the source code with our linear constraints, which leads to a competitive reachability. And also we are able to provide a better termination proofing and also be the first approach to LTL verification of Bitvector programs. Finally, it helps us to open a new path for the binary verification. Now let's go back to the previous example, and then let me show you how to apply our bitwise branching here. For the first one with a bitwise shift right, if we look closer, we would notice that with the condition s is greater than 0, this expression can actually be evaluated to 0. Therefore, we can replace it with this if condition expression. Going further, if the condition x is less than 0 satisfied, and then this expression is actually equivalent to 1. Therefore, we can further replace the previous expression with this new if condition expressions here. After this step, the previous program can be transformed to this one. Now, if we think further, we can actually generalize these rules for the bitwise right shift here to any arbitrary operators like E1 and E2. And once we have this condition satisfied, we can approximate this bitwise right shift with this integer here. Now let's see the second expressions here with the bitwise end. And with the condition which is true in this program hold, the expression is actually equal to the s and the 1 here. Therefore, we can replace the original expression with this if condition expression here. After the second step, and the bitwise branching can transform the program to this one. Following the same condition, we can also actually generalize these rules for the bitwise end here. For any arbitrary E1 and E2, if we have this satisfied condition, the bitwise and expression can be approximated by this mode expression here. Goes beyond to these examples, and then we came up with this theory of bitwise branching, and we provide two sets of bitwise branching rules here. The first one is rewriting rules to approximate the Bitvector expressions, and also another one weakening rules to approximate the Bitvector statement here. And there are more details about the rules in our paper. You are always welcome to check them out. Now let me show you the example, the experiment result for our reachability of the Bitvector programs. We contribute a two set of Bitvector benchmarks here. As you can see in the graph, the solid trends are the ones applied with our bitwise branching, and the dashed one are the ones with the Bitvector theories. Both results from these two sets shows that our bitwise branching can achieve comparable performance compared with the Bitvector series. Now you may wonder what's the case in the termination of Bitvector programs. Now let me show you a detailed example about the termination verification task here, along with our bitwise and positive rules here. For this program, the existing tools usually struggle to prove the termination of this program. They usually fail to show that the invariant is held inside the program because they are unable to reason about the bitwise end on the location 5 here. Therefore, like automate returns are null for this program. Well, now let's see, after applying our bitwise and the positive rules here, the source program will be transformed to the right side of this one with the if then else statement here. Now, the transition of this loop body will be transformed to this one T prime. And if we looking if we are looking closer, we would notice that the else branch where the bitwise end located is actually invisible from the loop entrance. And therefore, the tools can successfully show that the loop invariance is actually a hold for this loop body. Therefore, synthesize a ranking function R here. In the end, successfully prove the termination of this program. We also did a wide experiment on our termination benchmarks for the Bitvector programs. We contribute a new set of term bit benchmarks, and also compared with the results from the other state-of-art verification tools here. And as you can see here, the automate that applied with our bitwise branching can successfully prove the terminating and non-terminating benchmarks of the most of the case, while the other tools, they are either report unknown or timing out or fall into crash. Also, we contribute another two sets of Bitvector benchmarks for the evaluation of our bitwise branching for the LTL properties case here. Since there's no techniques can prove the LTL of Bitvector programs, the closest one is automate. As you can see here, the experiment result shows that the automate with our bitwise branching applied can successfully prove most of our benchmarks, while they fail and report unknown for the automate original branch here. And now I'd like to present to you our case study on the binary decompilation here. And there are various reasons that why we need to do a binary verification. And also there are open challenges in the binary decompilation here. And fortunately, we can leverage the existing tools to overcome the problems in the binary decompilation. But still, verification tools are struggling with the decompiled code, as I showed you here. And these decompiled code are heavy in nested bitwise operation here. However, with our bitwise branching, we can effectively prove the LTL property of these decompiled programs. And this is the experiment result for our LTL verification over the decompiled binaries. All these benchmarks are from the ultimate LTL repository, and we compile them directly from the source to binaries. Then we lifted them with our decompiled toolchain DarkSea. As you can see here, DarkSea with our bitwise branching applied can successfully prove all the benchmarks, while the automate report most of the benchmarks as crushed and unknown. Now, I'd like to conclude my talk as following. We first introduce source level bitwise branching and approximate the bitwise operation with our linear constraints. And also we did experiment show that bitwise branching can incur negligible overhead, and we are able to enlarge the domain of termination and LTL verification. And also we, in order to better evaluate the various verification tools, we provide a rich set of Bitvector benchmarks. In the end, we develop a binary decompilation toolchain DarkSea to help prepare the decompiled programs for the verification. Thank you for your listening. Now I'd like to take a moment to answer any questions you might have. Thank you very much.